equation. Okay, so one dimensional heat conduction for plane wall. So here we are going to derive the one dimensional heat conduction equation for plane wall. What is the equation? At last we will derive one equation. That equation or formula you need to remember to solve some small very easy numerical problems. Okay, so this is very fundamental concept. So in the syllabus, in the upcoming topics also related to this basic topic. So if we understand this clearly, then only we can understand the further topics. Okay, so first we have to understand this one dimensional heat conduction for plane wall. Okay, here one dimensional means only one axis I will consider. For simplification, I no need to consider all the three axes how the heat is conducting. For simplifying the numerical problem, I am assuming that heat is conducting in only one axis. That's why it is named as one dimensional heat conduction equation. And in which object it is happening? First I am taking in the plane wall. First I will make the diagram. So consider one plane wall. This is a plane wall. Okay. Suppose in plane wall, here this already we have discussed in the Fourier law of heat conduction equation, same thing. I will let you know how to derive this. Then the one side of the plane wall is at a temperature T1, another side of the plane wall is at the temperature T2. So what I said also, from heat will always travel from higher temperature to heat will always travel from higher temperature to lower temperature. Let the thickness of the wall as L. This thickness you take as L. Okay, now the thermal conductivity of the wall you take as K. This is the thermal conductivity of the material. Suppose this is one wall which has two sides. One side is at a temperature T1, another side is at a temperature T2. The thickness of the wall is L. The thermal conductivity of the wall is, or the object is, K. So every material has its own thermal conductivity, as I said already. Okay, due to that only the heat is conducting from one place to another place. So now you see the temperature is transferring, the heat is transferring from this place to this place. As we know already, what is the Fourier law of heat conduction equation? Q equal to minus K A into dt by dx. Okay, so to find out the one dimensional heat conduction equation for plane wall, this is the plane wall. Instead of considering the whole plane wall, I am going to consider one small section in the plane wall. Suppose this is the small section. For example, I am considering this small section, the cross section I am taking. This we take as dx. Okay, and the temperature at this point is T. This I am considering. So here I am going to find out the one dimensional heat conduction equation initially for this section. Then if I integrate to this section, then I can find out the one dimensional heat conduction equation for the wall which has the length of L. Instead of concentrating, I am just going to simplify and integrate. Then I will get the one dimensional heat conduction equation for this plane wall. Okay. Now why I have written this is dx? Because the distance is dx only. That's why instead of L I have written as a dx. Okay. Now how can I rewrite this again? So q is equal to minus ka into dt by dx. So this one I have to integrate. So I will integrate this one like I am just taking this dx to the left hand side. So this will become q into dx, which is equal to minus k. We know that the reason for the minus k, because heat is transferring from higher temperature to lower temperature, so the gradient is negative. That's why this negative symbol is I am putting minus k. K we know that thermal conductivity of the material into area. This dx already I taken there. So here dt only remaining. Now what I am going to do, I am going to integrate this x between 0 to L and this t between t1 to t2. If I integrate the dx with respect to in limits between 0 to L, this is x is equal to 0. This is x is equal to 0. I am considering only x axis. This is x is equal to L. So I am going to integrate this x with the lower limit of 0 and upper limit of L, and also this t with the lower limit of t1 and upper limit of t2, so that I will get the one dimensional heat conduction equation for plane wall. Shall we do? So you integrate, so that you will get integration of q dx between 0 to L. Again integration symbol, minus you take out, k into a into dt. Here integration between t1 to t2. Now you are going to integrate only dx, so q you take this side, so q into integration of 0 to L dx, which is equal to minus this dt only we are going to integrate, so minus k into a outside, the integration limit t1 to t2 into dt. Now we are going to integrate this dx and dt. It's a very simple integration, we have studied already. So q into, if we integrate dx, this will become x, limit lower limit is 0, upper limit is L, equal to minus k a into if we integrate dt, this will become t, so t1 to t2, lower limit is t1, upper limit is t2. Now again we substitute the lower limit, upper limit minus lower limit, q into L minus 0 equal to minus k into a into t2 minus t1. Suppose if I want to remove this negative sign here, I will replace this. Instead of t2 minus t1, if I write t1 minus t2, then this will become positive. So q into L minus 0 is equal to k a into t1 minus t2. I want only the q, so that is the heat conduction equation for plane wall. So I am just taking q left hand side, which is equal to k a into t1 minus t2 by L, or otherwise you can simplify again, q is equal to t1 minus t2 by L by Ka. So this is the one dimensional heat conduction equation for plane wall. This is important equation. Q is equal to T1 minus T2 by L by Ka, where you can say T1 minus T2 is delta T, L by Ka is R. R is nothing but conductive resistance. This we will study in the next topic, that is R is equal to L by Ka, which is conductive resistance. I will explain in detail about what is R. R is nothing but thermal resistance. Okay, thermal resistance formula is L by Ka. Like electrical students are studying electrical resistance, similarly here we are studying about thermal resistance. Electrical resistance is nothing but it is a restriction to the flow of current. Thermal resistance is a resistance to the flow of heat. That is the difference between electrical resistance and thermal resistance. Okay. For conduction, the conduction resistance is, conductive thermal resistance is L by Ka. So this is how we have derived it, and we have written that equation, which is Q is equal to T1 minus T2 by L by Ka. This is the one dimensional heat conduction equation for plane wall. Okay. Now next we will move into heat conduction equation for cylinder. Heat conduction equation for cylinder. Same concept, but object is cylinder. Instead of plane wall, now we are going to consider cylinder. Okay. So let us draw one diagram like cylindrical object. It's a hollow cylinder, okay, having two radius, common radius. Okay. Fine. Now let us consider the cylinder which has two radius. First one is, this is R1, and the second one is, this is R2. Okay. So suppose if the heat is here, the center point, from here to heat will travel to here, this from inner side to outer side. How the heat is transferring, I want to know. What is the heat conduction equation for this cylinder? We need to find out. Okay. So instead of taking this whole thing, I am considering a small cross section which has the radius of dr. This radius is dr. I am considering this small cross section which is dr. Again I am going to derive this equation, or I can directly write the formula for that, but you people will feel difficult to remember the formula. So if I derive it so that I can also explain you clearly how the heat is transferring. So again, to write the equation for this heat conduction cylinder, same formula we have to use for Fourier law of heat conduction, which is Q equal to minus Ka into dt by here dr. Okay, here instead of there we used dx, but here the radius is changing, that change in radius is dr. Okay. So same principle, you use Q into this dr, you take this side, dr equal to minus K into A into dt. Okay. So again you integrate this equation to find out that heat conduction equation for cylinder. So dr means the inner and outer radius is R1, R2. We have to integrate this R with respect to R1 and R2, and we have to integrate this Tt. Suppose this is at a temperature T1 and this is at a temperature T2. So we need to see the temperature with respect to upper limit and lower limit is T1 and T2. Now I am going to integrate, that is integration of Q dr, then minus K A into Tt. But this area, if we see this area of the cylinder, we have to write. So you take Q, let it be Q dr is equal to integration minus K, area of the cylinder is 2 pi RL into dt. So this is the area for the cylinder. What I can do this? So integration of Q dr is equal to integration of minus K into 2 pi RL. So how can I take this to this side and integrate this? So that again I have to take this R terms here. So if I take that R term here, then how it will become? So integration of this R already I have taken. So Q into dr divided by this 2 pi you take it. So, this r only will come here, which is equal to integration of minus k into this 2 pi into dt. Okay. Now, we have to integrate this. So, you take only you integrate the r. So, integration q you take this side, sorry, q you take this side, integration of this is equal to minus 2 pi k into dt. This integration between r1 to r2. So, q into, this is in the form of 1 by r. So, 1 by r if we integrate, that is ln of r, which is between r1 to r2, that is equal to minus 2 pi k. If we integrate dt, this will become t, then that is t1 to t2. Now, you just substitute. So, q is equal to ln of r2 minus ln of r1 is equal to minus 2 pi k into t2 minus t1. Now, again this equation I will write here, then I will simplify further. This very simple integration only. What is that? Q into ln of r2 minus ln of r1 is equal to, this minus I am changing into plus. So, 2 pi k, this L is also there, 2 pi k L, 2 pi k L into T1 minus T2. Okay. So, this in mathematics it is there one formula, ln of R2 minus R1, we can say ln of R2 by R1. So, Q into ln of R2 by R1 equal to 2 pi KL into T1 minus T2. I want only Q. So, what I can do? So, Q equal to 2 pi KL into T1 minus T2. So, divided by this ln of R2 by R1. Next, if I simplify again, how it will become? So, Q is equal to, this I am taking into denominator. So, T1 minus T2 by 1 by 2 pi KL into ln of R2 by R1. So, this is the final heat conduction, one dimensional heat conduction equation for cylinder. So, which is T1 minus T2 by 1 by 2 pi KL or ln of 2 by R2 by R1 by 2 pi KL. So, this equation also we should remember. This is the final equation. In any numerical problem, simple numerical problem, they will give us the problem and ask us to find out the heat transfer in the cylinder. So, that case you have to use this formula for heat transfer in the cylindrical one dimensional object. Q equal to T1 minus T2 by ln of R2 by R1 by 2 pi KL. Okay. So, where here this is as usual, this is delta T and this is R. So, the thermal resistance for cylindrical object is, the formula for thermal resistance cylindrical object is ln of R2 by R1 by 2 pi KL. This is the formula for cylinder. Okay. This is a one dimensional heat conduction equation for cylinder. Okay. Next we will see that one dimensional heat conduction equation, one dimensional heat conduction equation for sphere. Same diagram we will use. So, the object only changing, but this outer radius, inner radius, this change in radius also same. Again we will use the same formula, like that is Fourier law of heat conduction, that is Q is equal to minus K into A into dt by dr. Okay, if we derive and study in detail about these things, then we will never forget the formula. That's why I am deriving. Q is equal to minus Ka into dt by dr. So this dr is the change in radius here. Again, here itself I will write here area of the sphere minus K into area of the sphere is 4 pi r square into dt by dr. Okay, now what I can do? I can take this Q into dr by r square, okay, equal to minus K into 4 pi into dt. Okay, may I take like this? Yes, I can take like this. Now I will integrate. So this, if I integrate, then Q into dr by r square. Okay, next integration of minus K into 4 pi into dt. Okay, now this integration with respect to r1 to r2. So integration of r1 to r2 q into dr by r square equal to integration of t1 to t2, then minus k into 4 pi dt. So this you take outside. So q into r1 to r2 into dr by r square is equal to minus k 4 pi integration of t1 to t2 dt. So okay, if we integrate, then we will get final equation like q is equal to same t1 minus t2 by 4 pi k by r1 minus r2 by r1 r2. This is the final heat conduction equation for sphere. This is the final one dimensional heat conduction equation for sphere. Q is equal to T1 minus T2 by 4 pi K by R1 minus R2 by R1 R2, or otherwise you can take this R1 R2 here, R1 R2 into 4 by K by R1 minus R2. This is the final equation for heat conduction in the sphere. Okay. So these are the one dimensional heat conduction equations for cylinder. And sorry, cylinder, this is not cylinder, this is sphere. This is for sphere. So I will summarize the formulas. Okay, wait. This one we can summarize like here T1 minus T2, this 4 pi K, okay, sorry, this will become R2 minus R1 by 4 pi K into R1 R2. This is the formula. Okay, so this is the formula, sorry, T1 minus T2 by R2 minus R1 by 4 pi K into R1 R2. If we integrate, we will get, this is the final equation for sphere. So here also the resistance for sphere is R2 minus R1 by 4 pi K into R1 R2. Okay, so these are the one dimensional heat conduction equations for plane wall, cylinder and sphere. So the second topic also over. The third one is the resistance concept and electrical analogy for heat transfer. So this we have to see in depth. The third topic is These three formulas we need to remember, that is one dimensional heat conduction equation for cylinder, sphere and plane wall. The third topic is resistance concept and electrical analogy. So what is that? Resistance concept and electrical analogy. What is this? Resistance concept and analogy. So suppose if we take a wire, you take, this is one wire, okay, in which current is flowing, then that wire is made of one material which has some resistance, that is electrical resistance, okay. So this is one end of the wire, this is another end of the wire. Similar manner I will draw for my thing like thermal. This is one material, okay, which also has the same resistance like this, okay. Suppose if we take electrical thing, in the electrical thing what you can say, you people very well know, the current is flowing, here one voltage, here there will be another voltage, so there will be some change in the voltage which you can call as delta V. This is the electrical